Okay, so this is, yes, I mean, it's a sort of general title. It will be more, I mean, the content will be more specific. It's joint work with Martin Ripdahl and mainly supported by this TYPES project, this Horizon 2020 project. So I sort of have the feeling that all of you know this kind of, I mean, basically the fundamental theory behind all these early warning signals and precursor signals. So I'm going to be really quick. So it's I mean, there's nothing new in this here. It's the classical thing. We have a double fold sort of bifurcation. And we're looking at the double well potential where one state loses stability. And the question is how we can predict it. And I think a nice way to motivate the early warning signals in terms of raising variance and autocorrelation function is just to linearize around the given stable fixed point. And then, I mean, basically you see that you have a Ornstein-Uhlenbeck process I mean, locally. And this will then basically just from the fluctuation dissipation theorem, we know that the variance is somehow proportional to -1 over lambda, where lambda is the parameter in front of the x square. When we linearize the differential equation system, that means we're making a quadratic approximation of the potential well around the fixed point. And then on the other hand, the autocorrelation function is just given by this expression. It's all well known. And so as lambda, so in my case here, lambda now is negative. So as lambda approaches 0 from below, then the variance and the autocorrelation go up. So that's the classical early warning signals. And basically this goes back to the work by Kellen and Welton and Kubo in the 50s and 60s, but then of course has had these very interesting and nice applications in ecosystems and then later on in climate science as well. So yeah, so I mean, this works. It works for model systems. Here, this is just a simulation of this kind of double well potential model. And so the variance and autocorrelation go up. So let's see if it also, I mean, we've seen many examples where it works on model systems, on really controlled experimental setups. We've also seen that it works. Sometimes it has been criticized that it's really just a statistical thing. And in principle, you have this logical relation that if you have an imminent abrupt transition, then you will have the variance and autocorrelation going up, but not the other way around. So there is a bit of an issue about the predictive purpose, but there's also a bit of an issue about the fact that, I mean, what does it mean physically? And one observation is, so let's take a model, a quite general model of this form here, where we have the derivative of x given by some function f minus a control parameter p plus noise. And then really for all models of this form, then we can show that the variance is proportional to what I would like to call the sensitivity of the model. So basically we take the fixed point and the derivative of the fixed point x star with respect to the control parameter, take the absolute value of that, and then it can be shown quite easily that the variance should behave proportionally to that sensitivity. And this is of course nice because you can basically guess candidate mechanisms that might explain your early warning signals based on a nonlinear model. Basically, you guess the shape of f, and then you can check in your observations. You can check whether the variance is proportional to the sensitivity of that candidate model, and if it is, then that's a good candidate, and if it's not, you can throw it away. So let's apply this to the Greenland ice sheet, one of the often stated tipping elements in the Earth system. What you're looking at is from the IMBY team from this year, altimetry and surface measurements of the rate of the ice sheet height. You see that in particular in the central western part, we have significant reductions. There's always the concern that the melt elevation feedback might at some point kick in. Melt elevation feedback is just that, so you have melt, which means that you have height reductions of the ice sheet, which then, due to the atmospheric lapse rate, exposes the surface to even higher temperatures, and then you have more melt, and so this is a positive feedback. It's sort of a concern for the Greenland ice sheet. And so let's look at runoff, and basically, first, we're looking at melt reconstructions directly derived from shallow ice cores from this region here, and using those in combination with an ice sheet model and that original climate model, at a reconstruction of the whole Greenland ice sheet runoff. So the two direct, really observation-based melt records from shallow ice cores are in blue and in red, and the estimated runoff is in black. So this is the data. This is the detrended version where we took the log to make sure, because it has this tendency to have higher peaks to the more positive values. But so yeah, we played around with the detrending, and our results are not really depending on how we do that specifically. What you see on the right is on top is the variance, and on the bottom is the autocorrelation function. You see that they all significantly increase, where the significance test is a test where we basically randomize the phases in Fourier space of the underlying time series to account for both the variance and the autocorrelation, or the spectrum of the time series. So we have these early warning signals. So far, it's really just a statistical thing. And the question is, can we somehow add some understanding to that in terms of a model? And for that, we wrote down this very generic form of a model where the M is, M allows for a nonlinearity. We have the temperatures as the driving control parameter, and eta is white noise. And to your left, you see the evolution of the temperature. So the red line is the global mean temperature that you know quite well. And then blue and in black are two different observation-based estimates of the temperature development in Greenland, two different stations. And then what we do is we take the total mass balance data from reconstructions, which is basically accumulation minus the runoff and minus the ice dynamic discharge. That's what you see here in black. And then we take this model and do a complete Bayesian model calibration by using a so-called approximate Bayesian computation. So we simulate many times and just make sure that certain summary statistics are such that we say we are close to the model, and we only keep those parameter combinations where the summary statistics of the simulations are similar to the observed ones. And then we get time series that look very much like the observed total mass balance, which is of course here now, this is not surprising, the model is tuned to do this. It's just, it tells us that this form of a model, even the linear one where the M is put to 1, even the linear model can more or less reproduce the total mass balance evolution if you force it with the right temperature time series. And on the right, you just see the integration of the left-hand side to get the evolution of the Greenland ice sheet mass. So you see that it sort of increased well into the 20th century, then stalled for some time, and since 1930, a bit earlier, decreased for some time. And yeah, you see how it went. And all the different colors are different simulations of our model using different orders for the exponent M, as noted in the caption. So this looks like, so everything is just there. I mean, it's just a linear response. The linear model does quite well. It has fewer parameters, so it should be preferred. However, if we look at the potential of this model, and then the colored points here are the total mass balance reconstructions again. The red are corresponding simulations, now using a higher model order. The blue solid is the stable fixed point of the model, and the dashed one is just for completeness, the unstable one.
2 minutes, Niklas.
Yes, please.
2 minutes.
Yes, sorry, yes. And so what we do is, so for M larger than 1, and it doesn't really matter if you take 2 or 6 or 8, we see that so what we see in black here is the variance increase of the observed total mass balance. What you see in red is the corresponding variance increase of the simulations for a nonlinear model. What you see in blue is the sensitivity of the model. So comparing this to the case where we have M equal 1, we see that so the sensitivity doesn't change, the variance of the simulations doesn't change. So this is it's not in agreement with what we observe anymore. So this rules out the linear response, and instead tells us that there is a nonlinear model at work, nonlinear mechanisms at work that have the potential to destabilize. And of course, the question then is, what is the critical temperature threshold? And then you see here again in black the total mass balance values as a function of the sea level temperatures, together with their uncertainties. You see the different estimates for the fixed point, And all of them have, I mean, all of them correspond to a critical temperature threshold between 8 and 9 degrees. And if you compare this to the temperatures, then you see that, so this is this axis here. So we are almost at 8 degrees, so it's probably not too far in the future that we reach the critical threshold. And so I'm going to skip the AMOC just as a teaser. Similar things can also work for the AMOC. And so that to conclude, yes, critical transitions may be preceded by characteristic statistical changes that we relate to critical slowing down, the so-called early warning signals. And then the relationship between fluctuations and model sensitivity can really give us insights concerning the underlying physical causes. And we showed you significant early warning signals for the Greenland ice sheet and skip the rest due to the lack of time. Thank you very much.